It is on. Okay, so hello everybody. So we are now going to have the abstract interpretation session of VMCAI. So we are now, we have reached the AI part of VMCAI. So, and the first talk is about formal runtime error detection during development in the automotive industry. So this is joint work with Jesko, Hecking-Harbusch, Jochen, Quante, and Maximilian Schlund. And Jesko is going to give the talk.
Yeah, so thanks for the nice introduction and welcome to my talk. So my colleagues and I, we are from the corporate research division of Bosch. And you may or may not know our company from our consumer-facing brands. So here on the right side, we sell kitchen appliances, ovens, drills, stuff like that. But originally, and still mainly, we are also an automotive supplier. So in a lot of cars, you can find these boxes, which we produce. And these boxes are embedded systems, so they combine some software with some hardware parts. And as you see with these examples of an airbag controller or an engine control unit for a motorbike, it's very important that they behave in a safe manner. And this we call functional safety. And when you all know use cars, you just assume that it works. So we have achieved, or we do achieve functional safety. And one of the reasons is that we have very involved processes and standards how to ensure functional safety. And one of the recommended steps is to use abstract interpretation to prevent runtime errors. And I think it is a very good idea to do so because, your airbag should not crash due to an error out of bounds exception in the inopportune moment where you need it. And that's our overall goal that we try to achieve. But we face some challenges. So our code bases get larger and larger. So the C and C++ code we analyze becomes more and more because a huge part of cars today consists of code, and we only apply abstract interpretation in very late stages of development. So only in the very end, when everything is developed successfully and then plugged together, we get feedback from abstract interpretation, and this is often too late for the developers because they moved on or forget what they have forgot the details they have been working on. And we use a solution to solve these issues, which is to apply abstract interpretation on a module level. So instead of putting the entire code into the abstract interpretation engine, we split it up into individual modules. And at the intersection of these modules, we use contracts to maintain information that is needed between the modules. And this solves the problems we have been facing because by analyzing individual modules, we become more scalable because we give less or fewer smaller chunks of code to the abstract interpretation engine. And the contracts help us to stay precise because they provide further information than just the syntactic data types between the modules. And our developers have also the benefit that they now can just analyze an individual module and get feedback while they're developing. And in the main technical part of the talk, I want to give more details how we achieved this. So we built a framework given here in blue with which our developers interact. So from their point of view, not much has changed. They just give their code to our framework instead of an abstract interpretation engine, and then they get an output that helps them. And our framework uses under the hood the external abstract interpretation tool Astray. We could also use other tools, but yeah, we have a lot of good experiences with this tool. And the main technical parts of the framework are these two steps. So one, generating a verification harness, meaning going from the incomplete or from one module to some code that Astray can analyze, and also some automation to obtain contracts, because yeah, for legacy code or for large code bases, it is infeasible to write them all by hand. And yeah, now we will look into more details for these two steps. So generating a verification harness means, on a very high level, you get a module, and this module does not have a main function because yeah, the other parts of the code are missing, and then you have maybe contracts, and you want to obtain code that Astray can analyze. And we basically do 3 steps. So first we do some dependency analysis, which is similar to a compiler, just finding out what is there, what is missing. For the missing stuff, we need to generate stubs, which are just, which just for not yet implemented functions tell Astray how to handle them. And then we generate a verification driver, which actually uses the code in our module. And yeah, from these steps, 3 steps, we directly get the code which we give to Astray from the previous picture. Yeah, where we just only copy the code of the module under analysis in the middle. And next, I want to give an example how our verification drivers usually look like. So imagine you have a small module which has one global variable, an initialization function, and 2 public functions which are callable from other modules. And then our verification driver looks like this. So in the beginning, we initialize the global variable, and here we use Astray-specific instructions, which in this case set the abstract state of the global variable to full range. Then we call the initialization function, and down here we have a while true loop that simulates the continuous or the behavior of an embedded system, and just has a decision variable, which again is also set to full range, and then simulates all orders in which these functions could be called. And yeah, for each function we have one case. For the first function, the case is very easy because it does not take any parameters and does not produce a result. So we just call it. And in the second case, we need to initialize the parameters of the function, and then we also get a result. And now here you see a lot of full ranges, which probably makes analysis imprecise. And that's where our contracts come into play. So the idea behind contracts is to get more detailed information at positions where otherwise we would need to use full range. And I will illustrate the contracts we support by examples. So the first one are very similar to the ones we saw in the previous talk. And you can just specify preconditions and postconditions for functions. So for example, for a square root function, it makes a lot of sense to say that it only works on positive values and only returns positive values. Then in C and C++, arrays are often represented by pointers. So we need some kind of contract to say that we are dealing with arrays. So here we compare 2 chunks of memory, and we can say that pointer 1 and pointer 2 are representing arrays of a certain length. We have invariants for our global variables, and the last type is we can say which functions are part of the initialization of our verification driver, and which are called cyclically in the while loop. And now we will see the benefits of the contract. So for the example of the square root function, it on the one hand can give us a better stub if it's not implemented yet, where you can directly see how the precondition becomes an assert, so which is checked on the input, and then we generate a corresponding output to the post condition. And when the function is under test in our verification driver, then it is the other way around. So here we only give the appropriate parameters according to the precondition to the function, and then we check that the output fulfills the contract. And this way we also find out when a developer writes a contract by hand and it is not fulfilled. About the contract inference, I don't want to go into details, but refer you to the paper, or I don't want to get into the deep technical details and just explain it on a high level. So here on the left side, we have some external informations which we can just directly parse into contracts. And here we use contracts from results of previous runs of the abstract interpretation tool. So this means, we can find out how functions are used and actually use that for our contracts. We implemented all of that and used it on real code. So here is a very condensed version of the table from the paper, where we have 3 subsystems from a driver assistance domain, braking domain, and cruise control domain. And I only depicted the what is with 0. I depict when the entire system is given to the abstract interpretation tool, and with 1 I depict our approach. And you can see here that our approach finds fewer alarms, meaning that it automatically removes false alarms, which otherwise would be needed to be looked at by people by hand. And at the same time, we reach a higher code coverage. We were very happy with these results, and therefore, okay, this should not happen. You don't see it, okay. Sorry. Kind of being successful on our internal benchmarks, we gave it to actual running programs, to actual running development projects. And here is some embedded control software having 2 million lines of code in 3,000 C files. And with the low precision settings, they before us needed 3 days to analyze this. With high precision settings, I guess they aborted a run after several weeks. And we could reduce this to 12 hours when you add up the runtime for every module. And with parallelization, we could further improve this. And also the developers can now get feedback early during development and not in late stages as before. And the second real project we looked at was an embedded software library, which is a bit smaller. And here we have modules of 10 to 50 compilation units. And here we reach a very high code coverage of over 90%. And we find about 10 to 100 alarms per module. And all of these alarms have very short call stacks, because you can directly follow our verification driver to find out where problems occur. And this means that 10% of these alarms result in code changes, which is for our domain a very, very high number. So normally less than 1% of alarms would result in any code changes. And now you might think that this is a very buggy software, but in fact, this is not the case, but it's a library. And our tool or our framework is very good at finding cases where checks are not performed properly, because like we call every function in all these orders, and we will always find out cases where people don't do any checks that they need to do, and only other people intuitively use it in the right way. And yeah, we got feedback from the developers. So one thing is they just expect that our formal methods tools are centrally available and as automated as possible. So they don't want to do manual steps. They found our contracts intuitive because, yeah, I guess I showed you the examples and I get, you all pretty much understood them. And they also, or we achieved kind of a sweet spot in terms of our contracts, in terms of expressiveness for most cases and being easy to check. So stuff we cannot express is, for example, in an array, you could have the property that consecutive elements are always different, and this, yeah, you can't express with our contracts. The early feedback was greatly appreciated because, yeah, developers kind of found out that it's not some kind of certification step in the very beginning, but in the very end of the development cycle, but can actually give useful insights into their code. So to conclude, I showed to you how large code bases in the automotive industry are analyzed by abstract interpretation early during development. The tool the technique we used is module level abstraction with contracts, which is illustrated by this picture. And we had very positive feedback, and the rollout to more projects is planned. So thanks for your attention, and now I'm happy to answer questions.
Okay, thanks Jesko for the very interesting presentation. So how about questions? Patrick, and then David.
You told us what the developers liked. You did not told us what they don't like.
I mean, yeah. I mean, they don't like long runtimes. They don't like a lot of false alarms. Some probably would also prefer to not deal with abstract interpretation at all. Yeah.
There is no bug if you don't know.
Exactly. Yeah. Yeah.
David.
Hi, thanks for the talk. So you mentioned that you do not reach 100% code coverage. So what does it mean? Because you use an over-approximating static analyzer. So what does it mean?
Yeah, I guess that parts of the code are really not used at all and should not be there.
Okay. Dead code. It is dead code. You think it is dead code and.
I mean, it is some kind of dead code that probably, dead code searcher does not find. But because I assume they would look for that. But yeah.
I mean, another possibility is that you could have code that is behind some alarm where traces are cut. Like for instance, if you have some pointer error, Astray cannot quite make a state after that, so that could be the problem too.
Yeah,
so.
Precisely. So I mean, I showed, we also encounter definite alarms, as Astray is calling them, and we tell them they need to get rid of them before the results are meaningful. So yeah.
Okay, so one more. And in the meantime, I will have one while you give the mic. Did you look into relational specifications where you try to say if the function is called with an argument that satisfies this, you get some results that satisfy some other property?
We did
Input,
not.
output.
We did not. But
okay. Is it relevant? Or,
I mean, it's so from my perspective, everything making our contracts or specifications more expressive is relevant. But we need people to write these specifications in some way, and this is the difficult.
Thank you.
When you said that 10% of your alarms resulted in code changes, does that mean that the other 90% were false positive, or just that the developers didn't want to make a change?
Both. So
And do you have an estimate on
I have not.
how many?
I have
Okay.
not. But like, yeah, we can always argue why we don't do something because of an alarm.
So one related question, and then I let Patrick ask one, or go ahead.
Yeah, when you have people that do tests, they need more or less to know what is the test going to check. And that's very similar to writing a contract, in fact. And do you have people that do both test and contract and use both abstract interpretation and test on the same contract?
Right now we do not, but like, yeah, it would be a very interesting direction. And like, I mean, we have also people dedicated to applying abstract interpretation, and they oftentimes then write the contracts. And these people can be different from the developers. And then they add contracts which help everybody using the code, because the analysis gets more precise. Yeah.
Okay, so while I think we are going to move shortly to the next talk, I had a sidetrack question to the last one. So you mentioned 10% code change. Is there a percentage of specification change where people believe something on the program and changed their belief after the analysis, which could also be very interesting to report?
Yeah, I don't have any numbers, unfortunately, but I agree that this would be very interesting. Yes.
Okay, thanks again.